Welcome. Thank you for coming out. I'm really happy about this turnout and everything. I was looking at the numbers. I was like, 75 people. Oh, wow. Cool. But yeah, Kubernetes is definitely a hot topic that's going on in the industry. And scaling and making sure your application is available is one thing that is a common challenge for everybody. And like having this tool in place really helps out with that. So thanks for coming out. And this is my presentation, K8s and Heartbreaks, Introduction to Kubernetes. Is anybody in here a Kanye West fan? No, so you didn't get it. So I was trying to, K8s is the nickname for Kubernetes in the Kubernetes community. And 808 and Heartbreaks is the name of one of his albums. So like, did a play on that and actually took the color theme from there. Maybe the next crowd. But yeah, so yeah, I guess we'll go on. So I'll start off with going into an introduction of like the history behind containers and like, why we're going down this route with Kubernetes, and then talk about Docker, one of the leading container technologies out there. And then lead into in Kubernetes, where I talk about the pitfalls that Docker comes across that Kubernetes solves. And then I'll go into a little bit more detail about the Kubernetes architecture, so you can have a better understanding of its components, as well as like how you would ideally put your application into it. And then the benefits of Kubernetes, and I'll close out with questions and stuff. All right. So how many of you had to deploy an application before Docker or before any container technology? Okay, I see some vets in here. Awesome. Great.
Are there people who have not deployed on anything but Docker?
Or a container?
Oh my God.
Yeah, I had to go down and talk to people in those times and figure out like what was going on behind that.
I can't wait for 10 years from now when all of the senior engineers in technology never dealt with on-prem. Because I think we're going to see some game-changing stuff.
Oh yeah,
when
definitely.
that happens.
All the
Definitely.
serverless.
Yeah.
Like,
No,
yeah,
for
we
real.
actually use it.
Yeah.
Yeah.
Is that like one of those fun things?
Yeah. So so this section will basically be a brief history or brief memory lane. So in the first approach, we would call this the bare metal approach. You first develop your application on your local dev environment, your computer, and then when you're ready to move your application to production or onto your server, you do secure copy protocol, SCP, or a file transfer protocol, FTP, into your server that you have right next to you or on premise or wherever. And then in the process, you would pray that the deployment would go smoothly. So the setback behind that approach is that there's like, a drastic difference in the configurations of your environment, especially between your local and your production environment. So you'll have different operating systems, different dependencies, port configurations, secrets, all of that. And every update to your application, you run a risk of like having some downtime just in case any of those few components are not in sync with each other. So when it came to also handling large volumes of requests for this particular setup, you would have to plan for the number of servers that you'll purchase. So if you have an application that has 10,000 requests and you only have one server that serves 1,000 requests, then you have to like predict to buy like 10 or 20 servers to hopefully support that number of scale. So when you do that, you have to hire more staff to manage those servers. So you increase in money for managing those things. So you run a risk of increase in money as well as a chance of having your application down when following this particular approach. Then we move on to the co-location approach. So the idea to address this was we would purchase the server from somebody. So we'll eliminate the cost of managing and hiring people to manage those servers. And our new process would be we will develop our application in our local environment again. And this time we will SSH or secure shell copy into our off-premise server. And then pray once again that our deployment goes smoothly. Although we do cut the cost for like maintenance and hiring personnel for it, the deployment process still runs the risk of it being down because we still, once again, have the issue of having different operating systems, dependencies, libraries, secrets, port configuration, all of that. So this is where we move into the cloud, platform as a service. We didn't evolve to virtualization exactly. So we have cloud providers such as AWS, Azure, Google Cloud Platform, who allow us to have servers, to use the servers, physical resources, and use it to their full capacity. So this is where they handle the scaling part for us on our end. Therefore, our deployment process slightly gets improved, but we soon to realize that, how can we transport our applications without having to worry about the operating system again, or the libraries, the dependencies, all of that. So that's when container technologies came into play, and one of the most popular one is Docker. So Docker was first released in 2013, and it is a platform that helps developers build, ship, and run their application in any environment. So the ideal part of this Docker technology is to wrap a piece of software in a complete file system. And this file system will have your code, of course, the system runtime, your system tools, and system libraries. So it's a lot easy for us to port our application from one environment to another. But, this worked great until you come to the point of having to deploy hundreds and hundreds, or some people cases, thousands of Docker containers, just so you can handle the large volume of requests. So we will come across issues like complicated internal networks within Docker. You have unstable IP addresses. You run the risk of having some downgrades when you're trying to update a particular set of Docker containers, as well as, although they do have a very robust health monitoring for your containers, imagine doing that on a scale of like a whole 100 of containers and trying to figure out like, hey, are you alive or you're dead or some sort. So with those pitfalls, that's when Kubernetes came in. So Kubernetes, created in 2014, immediately after Docker. It is a Google open source project that enables developers to automate the process of deploying, managing, and scaling their containerized applications. So it can use Docker. Besides Docker, it can also be used with other container technologies like Rocket, Cryo, Kata, and Vertlet. So I would like to stress at this part that Kubernetes is a container orchestrator. A lot of people like to get it mixed up as regular container technology, but it is a container orchestrator. You can't really compare it with Docker. It's more of like it is a tool to another. So you will need Docker as the container technology that is used within Kubernetes, and Kubernetes is managing the number of container technologies, or number of containers, like Docker containers, within its entire infrastructure. Also, please do stop me if you do have questions, and if I'm moving too fast or speaking a little bit too fast. Okay, so now we're going to step into the Kubernetes architecture. So we can better look at this as two nodes. They start with two nodes, the master node and the worker node. So you can think of the master node as the brain, and then the worker node as like the limbs, legs, arms, and moving, the physical parts of moving, doing the heavy work for us. So let's step inside of the master node. And within that master node, there's the API server. And the API server is basically the central management entity that receives all of the REST requests for modifications. So it's basically the front end of the cluster. So this is where you would interact with your cluster to figure out what containers or pods or different Kubernetes objects are operating and get information about it, as well as deploy a couple of containers, or pods in this case, within Kubernetes.
Can I ask a question?
Mm-hmm.
Is the master node exactly the same as all the other nodes, except that it's identified as the master, and you can switch master nodes, or is there something different about the master node compared to the other nodes?
Okay, so the master node is gonna have four. I'm about to go over the main things within it, but the stuff that I'm about to cover in the next couple of slides are the very unique things behind a master node. So a worker node can't be a master node, because the master node is the brain of managing.
It's actually configured differently. It's a different.
Yeah, different type of setup. Yeah. So next is the scheduler. So the scheduler helps the Kubernetes help Kubernetes call the pods or any of the Kubernetes objects. And pods is one of the many objects that stores our application. It's basically the smallest form of a Kubernetes object within its entire architecture. The actual code would be within a pod, come to think of it. However,
Is a pod the container or?
I should actually go to pod is basically the Kubernetes object that holds our container.
So each, like one pod will.
One pod could have multiple containers. So I'll go into more detail a little bit later about that. But for the scheduler, one of the important things about the scheduler is that it creates the pods or creates the objects, the Kubernetes objects for us. And it does that based off the specifications that we created in our file about that particular Kubernetes object. Next, we have the etcd or etcd, depends on how you pronounce it. And that's basically a distributed key value storage that is used to store Kubernetes cluster data. So you want this part to be secured and nobody gets access to it. So this has it stores information like the number of pods there are, the states, namespaces, some passwords, and stuff like that. And it's only accessible by the API server for security reasons. And then we have the controller manager. The controller manager has a series of roles within Kubernetes, but its duty is to regulate the shared state of the cluster and perform routine tasks across all of the all of the worker nodes and within the worker node and stuff. So it serves as a watcher for the entire cluster, and it makes sure that it constantly maintains the desired state. So Kubernetes follows a declarative configuration and not an imperative configuration. So imperative is like more of like giving commands of like at this time you should have XYZ or follow these series of steps. But for declarative configuration, we're stating that at all times you want two containers that serve our front end running. And if at one point one of those containers go down, kick off another one and make sure it maintains that same state. So the controller manager would be like, part of that, and that's what Kubernetes, that's the type of configuration setup or philosophy that Kubernetes follows. And now onto the rest of the cluster. Within the cluster, we'll be talking about the worker node, the rest of the body. So the worker node has the kubelet. And the kubelet is basically the main service on the worker node. So the duty of the kubelet is to ensure the pods and containers are healthy and are running in the desired state, and it reports that back to the master node. And then we have the kube proxy, and the kube proxy is basically a proxy service that runs on each worker to deal with the host and subnetting and exposing the service to the external world, and it also deals with forwarding requests to containers across other networks in a cluster. And then we have the container runtime. So if you have your container in Docker, then that would be like Docker. If it's in Rocket, then it'll be in Rocket. And then we have the pods. So in this section, when I say pods, this could be another Kubernetes object, but like one of the smallest components within Kubernetes is the pod. So the pods generally hold one or more containers. So those multiple containers would be where your application would live in. And its ideal is to encapsulate those containers, the storage, the network ID, and other configurations that's needed for your container to run. So the other Kubernetes objects that we don't have displayed here, and there's like a whole list of it, we have services that acts as like load balancers, volumes, persistent volume or persistent claim volume to like store your data and hold it, labels, selectors, I'm missing another, replica sets, replica sets, and I'm missing one more. Operators. There's one more. I think I'm missing one more. Well, it's on the website, but depending on how you have your infrastructure set up. Jobs and daemon sets, there you go. Yeah. So the jobs and daemon sets might come in handy for people who are in data engineering. If you have data ingestion and you have like some script that you have to run to clean up the data before it gets ingested into another section of your architecture. But so that's the components that's within the worker node, and here's like a full diagram of like how this would look. So we have one pod that has one container, so one part of your application, And then another pod that has like 2 containers, which like will be both of your applications in one of them, depending on how your stuff is like set up. And the master node will communicate with these worker nodes where your containers are. And then the way how we would interact with it is with kubectl, which is Kubernetes command line tool, or you could go to the UI of Kubernetes. Like there's a port where you could go in and see what's running, as well as details on particular worker nodes and stuff. So why would we want to use Kubernetes? I mean, it is cloud agnostic, so you don't have to depend on a cloud provider like Amazon or, well, AWS, Google Cloud Platform, or Azure. So why are we going down with this technology? Why is this such a hot word? The reason why is because this tool helps us put a step closer to having a production-ready architecture. So the components or the key characteristics of having a production-ready architecture is stability, reliability, scalability, fault tolerance and catastrophe preparedness, performance, monitoring, and documentation, and security. I'm only going to cover 5 of these points due to the sake of time. Monitoring, documentation, and security would be like for another series of topics that we could cover at another time. But it's also important, especially the security aspect and documentation. I like to stress documentation a lot. But basically, when you have all of these characteristics, you're able to have your application encompass the 5 nines, which is 99.999% high availability. So with stability and reliability, you have to ask the question of like, is your container, is there a stable environment, stable deployment cycle for your containers, especially with your CI/CD tools? Are all requests to the containers returning a 200 status code? Like, is it healthy? And what happens when a particular container's traffic falls off? Like, what happens to it? So when we define stability, when we want to define stability as a way where the development, deployment, and adoption of a new technology or the decommission of old technologies does not increase the architecture instability. And when we want to define the word reliability, we can answer the question, can our containers be trusted with other dependencies in the entire architecture? So the way that Kubernetes addresses it is through its 2 layers of handling requests and its usage of objects for seamless deployments. So in the networking of Kubernetes, it has 2 levels. One handled in the master node and the other handled in the worker node. So inside the controller manager, there is a controller called the ingress controller. Its role is to handle and fulfill the influx of traffic that's coming in, ingress. And it basically acts as a load balancer. And then it handles the traffic and sends it off to the worker nodes. And then within the worker nodes, we have the ability to add in another layer of communication. And this is where the Kubernetes object service comes to play. So services are basically load balancers. And the reason why we have services is because pods are volatile. They will not be around forever. They'll die, and then we'll create a new one on the fly. So there isn't a stable IP address behind it. So to give some level of assurance, the service will act as a gateway, allowing pods to send requests to that service without needing to keep track of the physical pod and actually figure out what type of pods make up the service. So this is how a full diagram will handle this influx of traffic and make sure that, whatever request that we have, if a pod was to go down, the service object will handle like whatever traffic or whatever container that's under that service object, what other available container that's under the service object is able to send that off to.
Is that worker node, is that 2 worker nodes or is that 1 worker node?
Okay, it's 2 worker nodes, you're right. Yeah, okay, it's 2 worker nodes. Maybe I should.
Do the worker nodes, do those map to VMs or servers? Do the worker nodes, what are those mapped to, like in a physical space? Does that map to a VM, to a server? What are the actual things?
So the worker node will be like mapped to the master node, and then all this particular cluster right here, this would be within like a server.
Okay, so that would all be running on one server?
Yeah, like ideally. Yeah.
So like you could have a worker node as a VM or it's a bare metal server.
Okay.
You can have as many services and pods that will fit on it,
Mm-hmm.
or one.
Gotcha.
And then you can have more than one worker node.
Okay, so this is an abstraction.
Yeah, this is abstraction, complete abstraction. You can have like many worker nodes. I'm doing two for like, clarity.
Because of etcd, like we used to run our masters on separate nodes than the worker. We didn't care about our workers, but etcd restoration. It
At
was a while
scale,
ago.
you will want your etcd cluster to be separate.
Yeah,
Mhm.
than
we're shooting for that.
Okay.
A lot of memory.
Lots of memory. Any more questions?
So was
Mhm.
it basically the number of nodes that you use? Like you could, if you had a pretty strong, powerful machine, you could put a whole bunch of worker nodes into one
Mhm.
machine. But at scale, I guess at some point you might need more than one server.
Or if that node goes down, you lose everything, right? So.
Yeah.
When you get to performance, are you going to talk about how you tune these things?
Mhm.
Awesome.
Yes.
I have lots of questions about that.
Okay.
What about another question? How many working nodes can you have? Is there like a limit of working nodes that you can have in one server?
It depends on the server's resource. So like if your server has like a lot of like memory and CPU and all that good stuff, then it depends on that, as well as it depends on it really depends on the server's resources. So I'm trying to think of an instance. Yep. Yeah, it depends on the server's resource. Yeah. And then like you have to think about the resources that your own application takes that you have to also take into account. Another aspect that Kubernetes helps for stability and reliability is the way how you can do deployments. So take, for example, we have a worker node that has 2 pods with a couple containers in it. One pod has a UI container with a version number of 1.0, and the other pod has 2 backend containers with a version of 3.1. So our developers recently launched a new version of the UI container, 2.1.0. I know, massive jump. And we will need to update all of our containers with this version immediately. So an easy way to do this is to assign labels to those particular containers. So the way how we would do that here is we will actually have it under our metadata here. Actually, should move to the next slide. Yeah. So under metadata, app UI service version 1. So when we deploy this within our cluster for this particular container, the UI container, we're going to have these labels associated with it. So this allows us to search through the cluster, because we're going to have instances where we have like 100 versions of these, and we probably might have 2 versions of the UI running, depending on how you have your stuff set up. And so a way for you to not delete or remove the incorrect container or incorrect pod, you can assign labels to it, and then like you run an example command here where it deletes pods that have that particular label of service version 1 and app equal to UI. Fault tolerance and catastrophe preparedness. So when we talk about these 2 concepts, we have to ask, is our container healthy, and what happens to our container when it's like frozen or dead, and what do we do with the traffic that has fallen from that container? So Kubernetes has a built-in fault detection that occurs on the master and worker node. So for fault detection, let's take, for example, that same worker node with the UI back into containers, and the kubelet is checking on the status of those containers, and the kube proxy is handling the request between being administered. Then something randomly happens, like you forgot to close a stream, and the application just craps out or something, or just something random. There's always something that happens. So you have 2 containers, 2 pods that are no longer responding with each other, and we have in our health checks, and the traffic is being dropped. So our health checks are saying nothing, and they're saying like 404s or whatever, and the traffic is being dropped. So both the kubelet and the kube proxy become aware of this immediately. So they take this information and report it back to the master node and talk about its pod status. So within the master node, this information gets sent to the controller manager, and inside the controller manager, inside the controller manager, inside the controller manager, there are 4 different managers. There's also more different type managers, but the ones that we want to focus on in this case is the ingress controller, the endpoint controller, and the node controller. So the node controller receives this message, and both the ingress and endpoint controller reroute the traffic away from the following worker node. So it reroutes the traffic to another worker node that actually has the containers responding and working. And then next, the node controller eliminates that worker node from the cluster, and our scheduler will get this information about this new change, and we'll create a new worker node based on the configurations we declared. So if our pod configuration is saying that at all times we're supposed to have two worker nodes with like this type of setup, so that means like 4 containers of the backend and 2 containers of the UI is supposed to be running at all times, our scheduler will go in and make that update.
So one question,
Mhm.
with one of the previous slides, but you're going to update the version. Can you do rolling deployments where you can have some nodes have the previous version? And
Yes, definitely. Yeah, and rolling deployments and Kubernetes will have it in a way where it will continue sending those requests to those like the old version until it gets a cutoff date. Well, like cutoff time for like the last request, and then redirect the traffic to the new stuff. So like it will be like a seamless process and not just completely,
Are there ways to do that if you can't satisfy backward compatibility? Like, are there ways to say traffic from, traffic needing version 2 goes to version 2, traffic needing version 3 goes to version 3? Or does it only work well if you guaranteed backwards compatibility?
I think it works only well when you guarantee backwards compatibility.
You need a different strategy for the other.
Yeah, and then unless you have like a setup where the version 2 like front ends will only be able to read endpoints that like are directed to version 2 backends. Okay. So it's, like, it really depends on like how your team writes the software, and then how you have it set up within the architecture. But depends on like if you have your stuff set up for backwards compatibility. So I think that's like one thing that within my team at Atlas, we have to continue going on with like the backwards compatibility, because we do have some clients that's on the old version of our application. So we gotta make sure like our containers are able to like work with the old. Okay, awesome. So we're on to scalability and performance. So when we enter this realm, we have to answer these questions. And Kubernetes has the ability to solve it through horizontal scaling and resource efficiency. So that could be done with replica sets and deployments, as well as having some property within our configuration in regards to like the way how we use resources on our particular pod or Kubernetes object. So when we talk about horizontal scaling, we have to talk about having multiple instances of your application on one server. And then when we talk about vertical scaling, we talk about multiple servers with like, one instance of your application. So during the bare metal and co-location phases, horizontal scaling was rather difficult to accomplish. Now with Kubernetes, that's not the case, and this can be done through replication. This is done through the Replication Controller and a Kubernetes object called the Replica Set. So inside of the controller manager on the master node, there is a controller called the Replication Controller. The Replication Controller job is to ensure that the specified number of pods or a specified number of Kubernetes objects are running at any time. We can define the number of pods or Kubernetes object based on what we define our replica set configurations. So here's an example of how we would like define a replica set for our backend. So we would, in every Kubernetes configuration file, you have to specify what type of Kubernetes object it is, and you would do that with the kind property. So in this case, we have it set as the replica set. And then under specifications or spec, we tell them how many replicas that we want running at all times. So replicas for this instance is 4. We want 4 replicas running. So, oh yeah, they gotta define that stuff. So let's move on to the next part. Actually, does this part make sense to everyone? Yeah, okay. Yeah, I feel like I had missed something in here, but no, I covered it. Yeah?
So does that mean there are 4 replicas apart from the original container, or?
So if you're still trying to like apply this to like the previous slides, No, not really. So like if we just have like a whole new, completely new like cluster or whatever, we'll have completely new cluster, and we decide to launch this particular configurations of Kubernetes, then it'll have like 4. You know that pod object that had those, replace that word pod with replica sets, and it will have our containers in there. So we'll have like 4 of those within like basically 4 backend containers in there.
Right.
Yeah.
So what about the consistency between them? If I had to go and change something in one of the containers, then how would I, how would the change get replicated?
Wait, so like for example, when you say change one in one of the containers, yeah.
Treat the containers as immutable always.
Yeah.
You have to change them, it's a release. Change it, release it, and get all of them replaced through your automation.
Yeah.
You'll be so much happier.
Yeah, you know.
Deploying an image.
So the replica sets is just for scaling, right? So you don't
Yeah.
have the 2 worker nodes that one setup, but say if you find like the load balancer, I guess, right? You find that there's a lot. Is there some setup that I guess you realize that there's a lot more traffic that's coming in, and so then you just spin up.
Oh, okay. Oh, so you're saying like how does you handle the traffic between replica sets and stuff like that?
Or I'm trying to understand what a replica set is.
Oh, okay. So, how do I describe this? So there's certain features that a pod have that replica sets, a replica set have over a pod. So you wouldn't want to, like, if you wanted to make sure you have like constant scaling in the features within Kubernetes, for that you want to go with a replica set, and you have to say like, hey, at all times I want these numbers of like containers running. Unlike a pod, I forgot what was like the downfalls of like using a pod when you want to address like scaling concerns. But yeah, replica set, there's like additional features to it.
There's a selector. You can have selectors on the bottom of the spec.
But I thought you could have selectors with all like Kubernetes objects.
That's the difference between this and the replication controller.
Okay.
The older YAML file, basically.
Okay.
And something called replication controller. That doesn't allow the selectors at the bottom. So in here you can have selectors, and you don't really have to find the pod specification here. You can select all the existing pods and bring it as part of this application.
Okay.
And selector can be service. So you just say like I want 4 of my backend.
And okay. Yeah.
What kind of factors would you consider to come up with 4 as the number versus 6 versus 8 versus 50?
Oh,
Like
okay.
what kind of things do you think about to choose 4 replicas in a set?
For me, it would be on like based off of the container and the resources that my container currently takes for one series. Like, say I have a container that can only handle 15 users at a time, or 15 like 200 requests per second, and I know it takes out this number of resources and stuff. And then I do that based off of like what I project or what my application normally takes, and then like double it based off of that. So if my particular container takes 1 CPU unit and only handles like 50 requests and everything, and I know I get like 100 requests of things, I wouldn't go with like 4 replica sets. I would go with more. But I do it based off of like the number, like basically on the granular level of that container, and scale it based off of that. Any more questions? No? Awesome.
I have a question.
Mhm.
What is a replica? Replica?
Replica set?
Yeah.
Wait. This thing right here?
Yeah.
Replica set is,
Creating exact same copies of this.
yeah.
Oh, okay.
Yeah. Yeah. Okay. Makes sense?
Yes.
Yeah, okay. Thank you.
Thank you.
Sweet. Awesome. So besides horizontal scaling, Kubernetes has the ability to achieve resource efficiency. And by doing that with scaling up and down based off of the number of resources that's available on the hardware of where our cluster is living. So for example, take for existence, from 7 to 10 a.m. and from 4 to 7 p.m., our application receives like 100 to 200,000 requests per second. So that we would classify as high traffic for a particular application. And then for the other hours of the day, we'll receive 10,000 to 2,000 requests per second, low traffic. When this case happens for Kubernetes, it does two things. First, it does this horizontal scaling with the replication controller that we did in the previous slide. And then it actually makes use of the resource efficiency property here. So based off of the minimum and maximum that we define in our configuration, in this example under resource section, we have requests defining the minimum number of resources it can use in CPU and memory. And in our limit section, we define the max. So Kubernetes will have the controller shift the size of the replica sets when a certain threshold is being met. And all of this numbers are very arbitrary. It's not like, don't take it like to heart. But this is based off of like the size of resource that your cluster is living on for your server at the moment. So based off of the traffic, it will make that jump within the container. I mean, within the worker node for that container. Mm-hmm.
Do you prioritize, I guess they're all the replicas are the same. Okay. I was going to say, can you prioritize one service over the other? But that would be at the controller level.
Okay. Oh, so it's like, say for example, you have like, I don't know, the user API in one, and you want that to like always take up resources over another. I'll probably, in that instance, I'll probably define it in another replica set, and then like make sure like the resources would take that. Or, yeah. Oh, so overall, come to the conclusion. Overall, Kubernetes' unique architecture and built-in features help us achieve stability, reliability, fault tolerance, catastrophe preparedness, scalability, and I said scalability overall. No, I said stability. Sounds the same. And an improved performance. It's a step closer to us achieving the 5 nines for a production-ready architecture. Hope you found this presentation a little bit more informative and remove the black box that's over this tool in the whole 9. So yeah, if you have any questions, let me know. Sweet. Thanks.